A buffer is a solution that's able to resist changes in pH when you add either an acid or a base. So for example, in this generic reaction where I've put HA, an acid in water, if this is a weak acid and we have a significant amount of both the weak acid and the weak base, then if we were to add an acid, so that's like adding H3O+, if we have extra H3O+, it's going to shift the equilibrium back this way. So it's going to react with some of this conjugate base and push the equilibrium back to the left, which is going to consume some of the acid we just added. So it's going to minimize the effects of having added that acid. Meanwhile, if we added some base to this solution, it's going to react with the conjugate acid, HA, which is going to push the equilibrium to the right, which is going to produce some H3O+. So we've added base, but we're going to somewhat counteract that by producing some H+ in the solution. So a buffer solution is one where you have a weak acid and its conjugate base in both similar and significant quantities, and they are able then to resist changes in pH upon addition of acid or base. So when we say similar concentrations, what we mean by that is they can be up to a 10-to-1 ratio in either direction. So if you were to take the concentration of your conjugate acid and divide it by the concentration of your conjugate base, it should be less than 10 but bigger than 0.1 in order to have an effective buffer. Now, if I write out the generic acid dissociation constant Ka for this reaction, we have the concentration of H3O+ times the concentration of A- over the reactants, which is just the concentration of HA. We leave out the water. I'm going to take the negative logarithm of both sides. So we have the negative log of Ka is equal to the negative log of H3O+ plus the negative log of the concentration of A- over HA. The negative log of Ka is the pKa. The negative log of H3O+ is the pH. So this is pKa is equal to pH minus the log of the concentration of the conjugate base over the concentration of the conjugate acid. So overall, our pH is equal to the pKa plus the log of the ratio of the base over the acid. Anytime we have a buffer solution, so that is anytime we have a conjugate acid and its conjugate base present in at least a 10-to-1 ratio in either direction, we're able to apply this formula to calculate the pH of the buffer. This is called the Henderson Hasselbalch equation. Now, because in a buffer, both the conjugate acid and the conjugate base are in the same solution, they're always going to have the same volume. So there's another form of this formula, which is that we can say the pH is equal to the pKa plus the log of the conjugate base per volume, so that's moles per volume, divided by the moles of conjugate acid per volume. So we can cancel out these volumes and just say that the pH is equal to the pKa plus the log of the moles of conjugate base Cb over the moles of conjugate acid Ca. So when you're dealing with a buffer, and only when you're dealing with a buffer, you're actually able to ignore the volumes and just do the ratio of the moles of conjugate base and conjugate acid in this formula, or you can use the concentrations. Either are valid.